Hello to everyone from around the world, and welcome to today's webinar, Anatomy of Jitter, brought to you by Tektronix and EE Times. We have just a few short announcements before we begin. This webinar is designed to be interactive, so please ask questions at any time during the presentation by typing them in the text area and clicking the Submit button. Our presenter will answer your questions at the end of this webinar, but please enter them whenever they come to mind. Later in the program, we will ask you to complete a short survey. Please take a moment to fill this out and submit it. Your feedback is important to us and will provide Tektronix and EE Times with valuable information on the subjects covered in this webinar and how we can improve future broadcasts. The survey will open for you at the beginning of the Q&A session. Additionally, you can launch the feedback form by using the survey button. And now on to the presentation. It's my pleasure to introduce Jitter Lim, Senior Technologist in High-Speed Signal Analysis at Tektronix. Welcome, Jitter. I will now hand it over to you to begin the presentation.
Hello, I am Jitter Lim, and welcome to this seminar. Today, we will discuss the anatomy of jitter. In my 25 years in test and measurement, jitter analysis is by far one of the most requested, discussed, and debated topics. After today's webinar, my hope is that you will at least be clear about the different categories and types of jitter, their origins and interrelationships, and how they can be used to diagnose, characterize, and debug system hardware. And most important of all, how these various jitter measurements might be applicable to your specific application. In particular, I will make sure to leave plenty of room at the end of this presentation so we can get through as many questions that you might have. Since this topic is fairly complex, we only have a total of 13 content slides. The agenda for today: first, we need to get into why we need to perform and make these measurements. Next, I will provide a very quick overview of jitter basics. The first category of jitter measurements we'll discuss today are the fundamental period and frequency measurements. Next, we'll talk about a group of measurements called phase jitter measurements. Another category that we'll discuss is something that most of you are familiar with, called jitter decomposition. Next, we'll talk about what's commonly referred to as timing jitter measurements. Another class of jitter measurements that most of you are familiar with are eye measurements. Silicon folks in the audience will know this, and system integrators will soon need to understand how to perform BER measurements. Next, we'll talk about special cases of jitter measurements. For example, how to perform something called spread spectrum clocking analysis. After spending time on the different categories of jitter measurements, what I like to do is talk about how you can make the best jitter measurements, or optimizing jitter measurements. As I said before, the presentation itself will be very short, only 13 slides, so there'll be lots of time for Q&A because I know that this is a fairly complex topic, and there'll be lots of questions from the audience about how to make and how to understand and interpret some of these measurements. Jitter analysis is very important because it is fundamental to good signal integrity. If you work on some kind of a clocks, if you do some kind of a PLL analysis or design, if you work on a serial link, if you have systems that have clock recovery, you have to do setup and hold timing. You have to make rise and fall measurements. you are a candidate for jitter measurements. In all my years in this industry, I don't think I have seen a single application where jitter or timing is not critical. At a first level, jitter analysis provides pass-fail information. But more importantly than that, jitter analysis provides margin information. What this does, it gives you a better characterization, a better design that ultimately leads to reducing time to market, improving quality, reducing rework, and also field returns. So in the same sense that we spend a lot of time making very precise voltage measurements for signal integrity, the other dimension of signal integrity is timing analysis or jitter analysis. The basic definition of jitter is very simple. It is the deviation of an edge from where it should be. However, as we'll see, this apparently simple edge placement has evolved into numerous categories and different types of measurements. In this picture also you will see the variation in the edge placement. So jitter does not have to do with a single deviation, but a number of variations. And what's critical here is there is statistics associated with this variation. A peak-to-peak, an average, min-max, and standard deviation. This is a fundamental for truly understanding how to make proper jitter analysis. Period and frequency measurements are the most fundamental and basic jitter analysis. In every technology or standard that you look at, it requires that you perform some kind of fundamental period, frequency, or bit rate measurement. The key challenge here are not making the measurements, but the statistics associated with those measurements. For example, most customers expect to see a peak-to-peak measurement. However, a parameter, a statistics that's perhaps more important than peak-to-peak is standard deviation. The root cause for this is that peak-to-peak will grow with time, and the standard deviation number converges very quickly. Let me illustrate with an example. Let's assume that you're looking at characterizing a 100 megahertz clock, and the peak-to-peak jitter spec is, let's say, 100 picoseconds. You make a measurement on this clock, and you measure 99 picoseconds. Did it pass spec? It certainly appears that it did, because 99 picoseconds is less than 100 picoseconds. However, if you continue to wait longer and make this measurement for over an extended period of time, there's a very high likelihood that the measurement you make will exceed 100 picoseconds. Understanding that measurement variation is key to proper characterization of jitter analysis will allow you to properly characterize your boards with margin. So, in that example, in addition to making a peak-to-peak measurement, you might want to understand what the average frequency is, and in conjunction with that average, what the standard deviation of that jitter is. With the knowledge of the average and the standard deviation, you can predict or estimate what the worst case jitter might be. In applications where both edges of the clock or data are used, the width and duty cycle jitter measurements are required to ensure timing balance between the positive and negative clock edges. In PLL-based system, end period or end cycle measurements can be used to look for periodic variations in the systems. Cycle-to-cycle measurements are useful to ensure adequate setup and hold timing between consecutive clock cycles. Cycle-to-cycle jitter analysis can also be used to measure high-frequency cycle-to-cycle modulation within an SSC or low modulation system. For high-speed serial analysis, phase noise or phase jitter measurements like TIE or time interval error are extremely important. TIE measurements are also known as accumulated jitter measurements because they are measured relative to a forwarded clock or recovered clock. If you were forced to pick just one measurement for analysis for high-speed serial standards, it would be phase jitter measurements like TIE or phase noise. The TIE and phase noise measurements are related, and one difference between the two is that you can view the trajectory or time trend of TIE versus time. Another way to view phase jitter is through the use of a constellation diagram, where phase offset and phase noise appears as a spreading of the constellation points. This jitter family tree is one way to categorize different types of jitter. The first branch separates random, RJ, and deterministic jitter, DJ. The second branch separates deterministic jitter into data-dependent jitter, DDJ, periodic jitter, PJ, and bounded uncorrelated jitter, BUJ. The primary cause of data-dependent jitter, DDJ, is intersymbol interference, ISI. The terms correlated and uncorrelated indicate whether the amplitude of jitter changes with different transmitted data signals or data rates. That is, whether or not the jitter amplitude is correlated to the data. The key thing to understand is the reason for the jitter decomposition. There are two main reasons. The first is a language of communication. In general, correlated jitter can be corrected through techniques like equalization. In general, uncorrelated jitter cannot be directly compensated in an equalization system. The second reason for the decomposition is root cause. Understanding how the jitter is decomposed allows one in a system evaluation to determine what the root cause is. So generally, RJ factors come from silicon processes. Generally, data-dependent jitter, like ISI, comes from bandwidth limitations in the channel. Understanding these can help one determine where the resources should be spent to bring the overall TJ or total jitter budget under control. Earlier, we had talked about how parameters like standard deviation can be used to determine the peak-to-peak jitter. Total jitter is an example of an estimation technique. You may have heard of the term Dirac and an equation where TJ is approximated by 14 times RJ plus DJ. That 14 that you see that's multiplied by the standard deviation is an attempt to predict what the peak-to-peak jitter is by multiplying 14 by the standard deviation and adding the periodic jitter component to it. And so TJ, if you will, is close to what is traditionally known as peak-to-peak jitter, using some very specific formulas or estimations. Some of you may not be aware that rise and fall are jitter measurements. However, if you think about it, variations in rise and fall timing directly affect the timing of the edges and hence affects the jitter. Again, on these measurements you see on these slides, statistics are really, really important to be able to perform a rigorous analysis of these measurements. Similarly, slew rate is related to rise and fall times. The difference is that rise and fall times do not change with different amplitudes, but slew rates will change with the amplitude you're measuring over. Skew, setup, and hold measurements are critical in any digital systems that use clock and data. In the diagram you see over here, this is an excerpt from the JEDEC DDR spec, where there are massively parallel clock strobe and data lines. In general, my advice is to understand the measurements, the root cause of the measurements, and how they're performed. But for DDR, the measurements themselves are really not that complex. They're really essentially a whole bunch of different skew, setup, and hold timing measurements. In this particular application, one suggestion is that you might want to look at some of the custom software measurement packages available for you to make automated DDR type measurements, because there are lots of them. They can be fairly laborious to make. They're not difficult. It just makes it a lot easier if you had some of these automated solutions available. In the world of signal integrity, we make lots of different measurements like high time, fall time, rise time, peak-to-peak jitter, setup, and hold. The eye diagram combines a whole bunch of different signal integrity measurements and jitter measurements like rise, fall, peak-to-peak period, setup, and hold into a simple picture. Sometimes you also see an eye diagram with a keep-out region or a mask. The key to performing and understanding these measurements is to understand how the eye is created. For separate clock, forwarded clock, or discrete clock applications, you will use the clock to trigger the analysis and then view the data eye. For recovered clock applications, it is critical that you set up three things correctly. The first is you need to make sure that the loop bandwidth of the clock recovery is set up to the system you're looking at. Second, you need to set up the damping and peaking factor. And last of all, you need to set up the PLL order. Without fail, while looking at eye diagram measurements, one of the biggest issues I've seen is that folks are not setting up some of these settings to be able to recover and create the eye diagram. And what you have is either an eye that's open when it shouldn't be, or a closed eye when it should be open if you don't have the right loop bandwidth or PLL order. Now the next question would be, well, how do you determine what the setups are? The best thing to do, if it's available, is to ask for these settings from your silicon vendor. The next best thing to do is use the standard setup. If you recall the setups, many of these applications will actually set these up correctly per the standards requirement, because the way the standards work is that these are minimum requirements, and very often the silicon vendors implement clock recovery that goes beyond the minimal requirements. In all the previous slides, we've really talked about making jitter measurements on transmitters. In many ways, it doesn't matter how low the jitter is or how open the eye is if your receiver cannot recover and open the eye. So it really doesn't matter. For example, if the eye is closed, if the receiver can actually recover it and open the eye. So in some ways, characterizing receiver jitter can be more important than transmitter jitter. But how do you characterize receiver jitter? Well, for the longest time, if you look at the specs, in fact, if you look at the specs available today, you see words like TP4, jitter characterization, receiver characterization. Essentially, what you do here in these standards is you actually look at the input to the receiver. Fact is that these are really not receiver testing or receiver jitter. These are what's known as far-end transmitter eye testing. Receiver jitter testing has to do with stressing the receiver till you see an error or a bit error ratio or rate that fails a certain spec. Earlier, we spoke about how you can extrapolate to TJ using RJ and DJ. The unique thing about birds is that they don't miss any UIs, and they actually can calculate TJ directly, and from there estimate RJ and DJ. So it's a little different from the way you think of scopes, measuring RJ and DJ, and then extrapolating to TJ. A simplistic way to stress receiver testing is by varying the frequency and amplitude. However, in the real world, there are jitter stressors caused by, for example, your channel. Earlier, we spoke about jitter decomposition, or looking at how the different jitter is broken down into their various categories. In the world of DR receiver testing, we talk about jitter synthesis, or a jitter cocktail that consists of RJ and PJ to stress the receiver till it stops working. The diagram on the right is an example of that. It's also known as jitter tolerance, whereby for each SJ or PJ tone, you increase the SJ amplitude till the device fails. And once that's done, you move to the next tone, and again, you continue to increase that tone till the device fails. And you can just see a profile of how a receiver can deal with this. In many ways, you notice that it's inverse of what's known as a jitter transfer function, which we'll talk about in the next few slides. Now, let's take a look at some unique special cases and unique views of jitter. A view that should be very familiar to you is the histogram view. In the top row, we see the histogram view of a jitter distribution. On the top left, it's a very familiar view, a TIE histogram that shows a very Gaussian distribution of random jitter. That same view on a system that has deterministic jitter shows that it has a population that's distributed or focused on the edges of the histogram. So just looking at the histogram view will give you a very good qualitative feel for what the jitter sources are. In the middle row is what's known as a time trend plot. The vertical scale of the time trend plot is the jitter parameter. This could be TIE, period, frequency. The horizontal scale is time. So on the left, in the TIE time trend, you see what random jitter looks like in a time trend. It's spread and distributed evenly across time. On the right, you see a system where the jitter has a strong sinusoidal tone to it. So what you see then is that the jitter will vary in a sinusoidal manner with time. So on the right would be a view you might see if you have a spread spectrum clock that's implemented, or if you have some kind of strong modulation, let's say from a power supply coupling, you will also see that same time trend plot on the middle right. On the bottom left is yet another view. This is commonly referred to as the jitter spectrum. In this case, again, the vertical axis is jitter, but in this case, the horizontal axis is frequency. So again, when you have a Gaussian or random noise, it's spread out evenly across the entire spectrum. On the bottom right, you see the jitter spectrum when you have a strong modulation profile. So in this case, you probably see a spike, let's say around 30 kilohertz. If you have a 30 kilohertz modulation spread spectrum profile, or you might see 400 kilohertz power supply, switching supplies, or you might see, let's say, a gigahertz clock that's feeding through into your data signal. So these are very important views that allow you merely to diagnose and get a deeper understanding of some of the jitter root causes that may exist in your system. Here you see other views of special cases. In the top, you see a plot that's known as jitter transfer function. So there are two curves. There's one that starts off at 0 dB and drops off to the right. That's really what's known as a PLL loop bandwidth. So in a sense, the PLL is a low-pass filter. So it will track low-frequency modulation, if you will. The plot that starts off low and goes up to 0 dB is known as jitter transfer function. The net result here is that in a clock data recovery system, the PL inside will track and reject low-frequency jitter, hence the jitter transfer function is low, and what it is not able to do is track and reject high-frequency jitter, so the jitter is passed through. So that's why it's critical, as I mentioned earlier, to be able to understand what the loop bandwidth is, because it determines what jitter frequencies are tracked and what jitter frequencies are rejected. So that's the top trace and the bottom right trace. The middle bottom is a BER bathtub curve. The way you want to think about this curve is that it is directly correlated to the eye diagram on the left. You'll notice that the eye closure is not the same as the BER closure. The reason is because the BER closure is extrapolated out, so for example 10 to the 12, and the eye diagram is measured only up to 10 to the 5. If you were to go and look at the BER at 10 to the 5, you will see that it is directly correlated to the eye diagram closure. If you want the eye diagram closure to correlate to the BER at 10 to the 12, then what you need to do is run the eye diagram analysis till you get 10 to the 12 UIs, and then you will see very strong correlation between the eye diagram and the BER bathtub. So I spend most of my time in labs helping customers like you make these very precise measurements. And so one of the main challenges I find is the setup of the instrumentation is always not ideal. So what I like to do in this slide is give you some ideas about how to correctly set up the measurement instrumentation to make the best possible measurement. At the first step, most instrumentation you have has some kind of a one-touch or step-by-step jitter wizard. So my recommendation in general is that you use some of these automated, quick setup measurements as a first step to get you close to the optimal setup. I wish I could say to you that's all you need to do. Unfortunately, beyond that, you also need to do perhaps more optimizing depending on what your particular signal is. Once you've done that, you want to optimize for the highest measurement integrity. So, for example, if you're using a real-time scope, you might need to optimize and set the sample rate. You might need to set up and optimize the record length, the dynamic range, and the reference level. For example, customers will have situations where, depending on what they set the record length to, they will get different results. So a very common occurrence is that when you go from, say, 1 meg record length to 10 meg to 100 meg, you might get a larger TJ. When I see things like this, it's usually a clue that the jitter has some kind of a low-frequency modulation, such that as you capture more and more cycles of this periodic modulation, you get a larger TJ number. So it's key that you understand how these measurements set up and to understand why they will change depending on what the setup is. We talked about it earlier. The one-touch wizard will set, for example, the clock recovery to a mean clock. That's a great thing at the first step. The reasons when you look at a signal for the first time, the recommendation is that you do not immediately go and start recovering the clock, because you might want to see what other modulation profiles exist. So setting a mean clock is a great way of doing some basic troubleshooting in debug. However, there are two issues with this. Number one, the mean clock is not how the standards and how the silicon works. And number two, sometimes if you have high levels of low-frequency modulation, for example, if your system implements spread spectrum clocking, the mean clock cannot create an open eye. In that case, you have to use a reference clock. In a forwarded clock system where the clock is available, you should use the explicit clock to trigger the signal. But for most high-speed recovered clock systems, you need to use what's known as PLL clock and set the loop bandwidth and the PLL order to be able to get the right eye opening. I mentioned this earlier, and I'll say this again. You can be very careful about using the instantaneous and peak-to-peak jitter measurement results. The risk with that, as you know, is that the instantaneous values and peak-to-peak results will change with time. So when you write or create a document or a jitter characterization report, you might want to capture how this measurement is done. For example, you might want to say, this measurement, this peak-to-peak measurement of, let's say, 99 picoseconds was made with a population size of 10,000 after a period of so much. But you might also want to add the standard deviation for these measurements is at X. And the reason is your customers can then use the peak-to-peak results, the population, the average, and most importantly, the standard deviation to be able to predict what your system might do. Another way to do that is to use values like TJ and RJ. Again, those techniques, these dual direct results, for example, have these statistics embedded into the results. So the TJ actually has standard deviation information already embedded. So that's another technique to be able to document your jitter analysis results. There are other techniques, for example, to help you improve your jitter analysis debug. So, for example, there are ways for you to sync to the waveform. So, for example, if you have a specific TIE or cycle measurement that has a high value, there are ways to be able to go from these views directly to the waveform view to correlate between why, for example, you might see a high TIE. And you will see in most cases, you'll find that the correlation will, for example, show up at the end of a long run length, long ones or 1 zeros. You'll see this high jitter. Or, for example, if you have something, for example, they call it a lone bit pattern, you will also see some of these occurring. And then again, some of these tools have the ability for you to save the worst waveform feature. So if you run an analysis overnight, capture lots of data, there are tools that allow you to save the waveform with the worst failures, so you can go back and see what exactly happened on that specific acquisition. Jitter, as we know, is a very complex topic. There's lots of information online. You can always go to www.tektronix.com/jitter. There are a significant number of app notes written on a whole bunch of different jitter topics. Advise you to do some research on some of these online sites. There are resources available. You certainly can speak to your Tektronix field application engineers, many who are experts on this topic, to help you understand some of the different measurements and how they might apply to your application. And so with that, we are at the end of the content session, and let's go to the Q&A session now.
Thank you, Jit. Before we start the Q&A, please note the survey on your screen. And if you do not see the survey, please launch it now by clicking the survey button on the left side of your interface. Thank you in advance for filling it out. Your responses are very important to us and will provide Tektronix and EE Times with feedback on how to improve future webinars. We will now move into the question and answer section of the presentation. So if you have a question for our presenter, please submit it now by typing it in the text area on the left-hand side of your screen and click Submit. And with that, I'll hand it back over to our presenter to kick off the Q&A.
Thank you. And I see there are a large number of questions, so let's try and answer all of these if we can in the time frame. So let's see. The first one is, what equipment do you have that makes the BER measurements? So the first thing you got to think about when you talk about BER measurements is you need to understand if you're trying to make a transmitter BER or a receiver BER measurements. They both are trying to achieve the same goal, but they're really quite different measurements. So if you're trying to make a transmitter BER measurements, and this is very often called out in the specs. So if you see in your spec something like TJ requirement, then that usually means that the spec wants you to make a transmitter BER measurement. And in that case, there are software packages in various scopes that can make that measurement. There are also the idea of a receiver BER measurement. In that case, what you use is a pattern generator with error detector to be able to put a pattern into the receiver and then to loop back and read the error bits, if you will, that come back from the receiver. So they both achieve the same objective, which is making a BER measurement, but they both do it in a quite a different way. Okay, so the short answer is there are scopes and scope software that will make a transmitter BER measurement, and there's a bird scope product that will do a receiver BER measurement. Okay, so let's go to the next question over here. The question here is, what jitter noise floor can I expect from your, let's see here. Can I expect from your 50 gigasample DSA 71604B over a 10 kilohertz to 1 megahertz filter range? Are there tables that list the J and F for various filter bandwidths? Okay, so the spec on this instrumentation shows jitter noise floor over the entire bandwidth range. So this particular instrument is a previous generation, and I believe it's 16 gigahertz. So I expect that the spec will say something like the jitter noise floor over the 16 gig range is something in the order of 300 or 400 femtoseconds. So that's the entire broadband range. So I do not believe the spec will have jitter noise floor for the various filter bandwidths. So one thing you can try and do to determine that is to put in a broadband filter, and there are tools in the instrumentation that will allow you to high pass and low pass such that you can get the 10 kilohertz to 1 megahertz filter range. So there are tools that allow you to do that and characterize within this, if you will, a band pass filter range. And for customers in the computer world, for example, you only see perhaps only a low pass or high pass function. This is applicable for many of the communication standards, the need to do a band pass filter, if you will. Okay, so that's where the questions came from. The next question here is, why is the jitter transfer important? So what I like to do is, let's find the slide that shows the picture. So I'm going to figure out how to show slide number 12. So let's see here. Let me figure out how I can push slide number 12 to the front. Well, thank you. Thank you for doing that. So in this picture, the jitter transfer function is seen in the top schematic. You have this trace that goes from the a low attenuated on the left to the right, and then you have a function that goes from the left to the right. The reason that plot is very important is because it shows you the ability of a receiver to recover the clock and determine the zeros and ones. So on the left side of the jitter transfer function, it shows shall we say, a strong ability. The receiver has a very good ability to track and reject the jitter, which means that you will have a good likelihood of seeing or recovering the data. On the right side, the high frequency stuff, the receiver will struggle to recover the data. And usually in the middle, there's shall we say, an amplified jitter also. So the reason why the jitter transfer function is very important is because it's really a plot that tells you the ability of a system to be able to recover the data from what's received. So that's the main reason for having the reason for having this thing called a jitter transfer function. Okay. So let's go to the next question over here. So the next question is, can you explain the difference between the low pass and high pass jitter transfer functions through an example? Can you explain the difference between the low pass and high pass jitter transfer functions through an example? So this would be related to this plot over here. So let's think perhaps about what the root cause of why someone would want to do that. So I don't have a picture of a low pass jitter transfer function, but let's think about the root cause here. So the reason for a high pass transfer function is because at the low end, the CDR will track and reject the jitter. The reason for a high pass function is that the PLL behaves differently. So if you have a PLL that rejects this high pass, so if you think about PLL, it's a low pass filter. So if you send a clock system, for example, through a PLL, guess what? In that case, it rejects the high frequency jitter. So that's one example where you have the ability for CDR to high pass, track, and reject low frequency jitter, and the opportunity, if you send a clock, for example, to a PLL to actually low pass or reject high frequency jitter. So hopefully that answers the question about the difference between a low pass and a high pass jitter transfer function. The next question here is, what are the different causes of jitter? So one way to think about this would be to go to, let's go to slide. Let's try and push slide number 7 through, please. Slide number 7, the one that says jitter decomposition. Thank you. So the first level of looking at root cause of jitter is to look at the separation between RJ and DJ. So let's look at one leg of this slide here, which is the RJ or random jitter piece. So this usually comes in general from silicon effects. So this is things like white noise, flicker noise, short noise from the RJ. And so really what you're asking for is, well, how do I fix this? So commonly, to be able to reduce RJ, you want to be able to look at things like your crystal oscillator. That's one of the causes of RJ. You want to look at the chips, the silicon that's used in your PLL design. That would be a cause of RJ. So when you think of RJ, one of the larger contributors is can you put a different piece of silicon in there to be able to do that? Let's look at the other leg of the TJ, and that's DJ or deterministic jitter. Okay? The biggest root cause there is the channel or bandwidth limitations in the channel. So if you want to look at improving the DJ, one clear example would be to increase the overall bandwidth performance of your channel, because the ISI or the bandwidth restriction of the channel is what causes the DJ phenomenon. So if you can have a higher quality cable or connector, a riser, a PCB, that would significantly improve the DJ contributor to jitter, and it also will affect something called DCD, which is also somewhat related to ISI. So hopefully that answers the question about the different causes of jitter, and also where you might look to find some of these root causes. Okay. The next question here is, when setting the clock recovery parameters in a scope, what are we trying to match? The silicon PLL on the receiver side, in the CDR loop parameters other? So the answer is, when you're trying to set the clock recovery parameters in a scope, you are trying to match the receiver silicon, okay? So when you say you are using the scope, what this means that is you are making some kind of a transmitter type measurement, number one, and then when you look at all these different parameters, like what do you say here, the silicon PLL, the CDR loop, you're trying to make the scope behave like a receiver. So in the same sense that the receiver has a loop bandwidth, it's got a PLL peaking factor. It's also got what's the third one here? A PLL order. What you're trying to do in the scope is that you're trying to make the scope behave like the receiver. That's a great question, because probably more than any other challenges I see out there, the setting of these parameters makes the difference whether you have an open eye or a closed eye. So the short answer to your question is you're trying to match the silicon receiver when you set up those parameters. The next question is, I'm using DPO jet of Tektronix on DPO scope. Where can we change the clock recovery method as mentioned in your last slide? Okay, so I believe if you go to that menu, there should, first of all, you got to pick the measurement you are setting. So you're probably using, let's say, a TIE measurement. If you go to the TIE measurement, there should be a configuration tab, and within the configuration tab, one of the tabs should say clock recovery. And so there should ultimately be a clock recovery tab that allows you to set the various parameters for the clock recovery. Now, the other thing that's available is I know for a fact that once the webinar is done, my email address will be sent as part of the communication. So if this doesn't answer your questions, you will get my email address. So if I don't answer your questions today, you still have a shot by getting my email address. Okay, the next question here is, RMS jitter may depend on 1, PLL setup, analog or digital, 2, phase detection circuitry, 3, phase noise of the active device, 4, bandwidth LC circuit, Q of L and a varactor C or digital delay, 5, clock embedded in data and recovered or clock locally generated independently, 6, phase noise is a function of offset from carrier frequency. How does this translate to jitter? Can you please comment? So let's see. Let's see if we can get a phase noise plot to show here. The closest phase noise plot we have would be on slide number 6. Can we push slide number 6, please? The title is Phase Jitter Measurements. Thank you. Okay, so if you look at the top right picture, you actually see what is close to a phase noise plot. So this is the diagram on the top right. So what you want to think about this is, the way to think about this is that the vertical axis would be the amplitude of jitter, and as you go to the right, offset from the center frequency is the offset. So the phase noise measurement is usually defined at a specific point at a specific offset, let's say 10 hertz or 100 hertz from the center frequency. That's one point. So that's how one thinks of phase noise. But I want you also to think about the entire shoulder, if you will, on the right side. So even though phase noise focuses on a specific offset, but if you look carefully at the shoulder, there is a whole bunch of frequencies that live on the other side of this offset. So if you think about it, all those frequencies exist even though the phase noise measurement only looks at a particular point. So the way to think about it is that all the other points at 1 hertz, 10 hertz, 20, 25, all are different jitter frequencies, if you will. So the way you want to think or correlate from the phase noise measurement, if you will, to jitter is think of phase noise at multiple offsets. And all those other multiple offsets are also jitter components. So again, the difference here is in this plot, when you make a phase noise measurement, you can very precisely average this plot and know what a tone is, an offset from the frequency. But What you do not have is a trajectory. In other words, let's say you have a 10 hertz offset, but what you don't know is how it's changing with time. And so that's one of the benefits of having a time trend view. So hopefully that answers your question about how these measurements will translate to jitter. And again, if I don't, please feel free to email me directly. The next question here is, can you accurately calculate BER from TJ measured at the output of the transmitter phi? Or conversely, for a target BER, like 0 errors over 3 days for a particular high-speed phi, like 8 gig fiber FC, can you determine what the TJ must be at the transmitter output of the phi? So these are almost the same questions. So the first question, can you accurately calculate BER from TJ measured at the output of the transmitter phi? So the answer is yes, you can with the following setups. If you make a TJ BER measurement at the transmitter to correlate it to the transmitter phi, these are things you must set up. Number one, you must try to make sure that your clock recovery is as similar as possible to the receiver silicon. So we talked about this earlier. You want to try and make sure the loop bandwidth matches your receiver. You want to make sure the peaking and damping factor try and match your receiver. You want to try and make sure the PLL order matches the receiver. So that's one part. Remember, though, this is still an estimate because these functions you see here are linear estimations, and most receivers are much more complex than these setups, okay? So that's step one. The second part is you got to make sure that you know what the TJ peak max spec is. The reason is because the reason is because the making a TJ measurement without knowledge of what the peak to peak or the max spec is for TJ is irrelevant. Why? The reason is because the receiver could have things like equalization. Okay? So for example, let's just say you actually make a TJ measurement at BER and the eye is completely closed. The TJ is bigger than the UI. Well, does it mean that the part has failed? No, because there is some likelihood that the receiver can actually equalize and open up the eye. So the other thing you want to know is, does the receiver have equalization? And if it does, you also want to equalize the eye before you make the measurements. So the short answer to the first question is that if you get all the parameters right, the loop bandwidth, the equalization, the PLL order, the maximum spec, if you do all that, then you have a very high likelihood of calculating the receiver BER from making a transmitter BER measurement. The second question is, for a target BER, like 0 errors over 3 days, can you determine what the TJ must be at a transmitter output of the phi? So again, very similar. You can do almost the same thing. And what you can do is, as you characterize the TJ, you want to make sure what the correlation is to the BER receiver. So again, like the first question, the key thing is to understand what the receiver silicon is doing. Now, your next question might be, well, how do we know? The best thing you can do is to call your silicon vendor and ask them, what are these setups I need to dial into this instrumentation? And if they give you the information, that's the best. The problem with that is twofold. One is they are most likely reluctant to give you the information because that's the secret sauce or IP that makes the differentiator between your silicon vendors. The second is it's not that they don't want to, but their receiver is much more complex than just saying that it's got a loop bandwidth or a peaking factor or PL order. These are fairly complex setups. So that's one challenge you might have. What is the second alternative? The second alternative is to go in there and look at the standards. If you look at the standards document, you will see jitter transfer functions, loop bandwidth functions, PL order, etc. So you can dial those into the setups because, in general, that is a minimum required spec. The silicon vendor will almost always put in silicon that is better or much better than what you see in the standards requirement. Okay, so that's the best approach to use. The next question here is, what is the difference between peak-to-peak jitter and cycle-to-cycle jitter? So let's try and push slide number 4 onto the screen here, please. Okay, so peak-to-peak jitter is really a statistics definition. So when you think of statistics like average or standard deviation or min or max, well, peak-to-peak is really max minus min. So on slide number 4, it's really the difference between the, shall we say, the worst case measurement, whatever it may be, period frequency, minus the smallest. So that's peak-to-peak. It is a statistics. So you could have peak-to-peak for cycle-to-cycle, peak-to-peak for period, peak-to-peak for period. It doesn't really matter. It's a statistics. What is cycle-to-cycle? Let's see if we can push slide number 5 onto the screen, please. The next slide, slide number 5.
It looks like this is probably the last question you'll have time to answer. We've hit the hour mark, so go ahead and finish up this question and leave us with some final remarks.
Okay, thank you, and I'm sorry I ran out of time here. I guess I didn't give enough time. So slide number 5, cycle-to-cycle is defined in this case to be, if you look at the diagram to the bottom left, it's P2 minus P1 or P3 minus P2. That's a cycle-to-cycle jitter measurement, and it can have peak-to-peak, and it can have standard deviation. So cycle-to-cycle is a type of measurement, and peak-to-peak is the statistics related to the type of measurement. And remember, you will get my email address, so I'm sorry we're out of time. Thank you, Jessica.
Thank you so much, Jit. I would like to thank everyone for attending today's webinar, Anatomy of Jitter, brought to you by Tektronix and EE Times. Please fill out and submit the survey at this time if you haven't done so already. By completing this survey, you will provide Tektronix and EE Times with valuable feedback on the subjects covered in this webinar and how we can improve future broadcasts. This presentation will be available shortly in an on-demand format, and as a registered user, you will receive an email with detailed information on how you can access the on-demand replay of the webinar. The on-demand will also include a PDF copy of the slides used in today's discussion. This webinar is copyright 2010 by EE Times. The presentation materials are owned by or copyright by Tektronix, which is solely responsible for their content. The individual speaker is solely responsible for his content and opinions. We hope you will join us for future webinars. For our current schedule of live and on-demand events, please visit us at eetimes.com. Thanks for joining us and have a great day.